Hi, I'm Florence Leong, a postdoc in MorphLab, Dyson School of Design Engineering, Imperial College London. My team and I are working on a RoboPatient platform for abdominal examination training. This project is in collaboration with the University of Oxford and the University of Cambridge, funded by EPSRC. In my current research group, I'm also collaborating with colleagues from University College London. Today, I'll be presenting on the development of a real-time augmented reality RoboPatient platform with haptic feedback using a 3D surrogate model trained by machine learning. Before I go into the development phases, I would like to do a brief intro and motivation of my work. So, when we visit a GP with abdominal discomfort, the GP would physically examine us using procedures such as abdominal palpation to feel if there are any anomalies within our abdomen. In this video, this is our clinical collaborator, Professor Simon de Luzigno from the University of Oxford, performing abdominal palpation. So this procedure is actually highly complex and it takes years of experience to grasp, especially with multiple motor sensory systems involved, such as touch, where we feel the texture and stiffness of tissue, as well as patient's motions, such as muscle contractions, sound, such as auditory and verbal signals, and sight, by observing patients' facial expressions or subtle reactions. For medical students or trainees, without any prior knowledge of the patient's condition, it would be a big challenge for them to even know what to feel for. It takes lots of time and practice to be able to improve their skills, usually based on their own observation and the trainer's feedback. Current training platforms such as mannequins mostly provide them with feedback such as haptic, which isn't really obvious. Training on actual patients with actual conditions would provide the best training experience and outcomes, but it is not always possible as it'll cause more discomfort to patients. These challenges motivate us to develop a RoboPatient training platform, which in my scope provides additional visual information for trainees to understand what happens beyond the skin during palpation. The projection of stresses of internal tissues onto the training platform would allow trainees to regulate their palpation force, at the same time sharpen their finger sensitivity. The RoboPatient platform is also highly configurable to emulate different tissue conditions, such as masses or tumors with different tissue stiffnesses at different locations. With the introduction and background, I'll now move on to my work on the development of a surrogate model trained by machine learning to be incorporated with the RoboPatient platform for real-time haptic feedback and the projection of internal stresses onto the platform. I'll briefly share the details of each developmental stage. So firstly, the process started by obtaining a 3D abdominal model from a set of CT scans using this XCAD program by Dr. Paul Sager from Duke University. This model is segmented and meshed into a high-fidelity finite element model simplified for the abdominal palpation simulation. I'm currently focusing on the liver for visualization. So the simplified model consists of a lump abdominal tissue and a ribcage assigned with the material properties from the Global Human Model Consortium, GHBMC, and the liver with validated Ogden model and Prony series parameters from the literature by Sato et al. A dummy finger model is also added onto the model to visualize the finger palpation and contact forces onto the abdomen. So the palpation simulations are set up to build a design space for the 3D surrogate model, focusing on the effect of palpation onto the surface edge of the liver, comprising 377 elements. This is done to reduce computational speed for this proof of concept in the FEM simulations and machine learning, and it'll be then extended to a full model of in our future work. The simulation is performed on 25 locations above the liver, depicted by the red crosses, with finger indentation up to 15 cm onto the abdomen. And the finger contact forces and the stress tensor of each element on the liver edge are recorded. The maximum principal stress on the elements are then computed. So this information will serve as the training input and output to the neural network, which forms the machine learning process. So this is one of the results from the simulations I performed with the finger above the central edge of the liver. We can see how the internal stresses on the liver increases as the finger indents deeper. All the input and output data of the simulations are consolidated to form the surrogate model for the machine learning. From here, input data, which are the finger XYZ positions and the contact forces, are fed into the neural network as training inputs, while the computed principal maximum stress on each element is given as training output. The multi-layer perceptron network implements the gradient descent, specifically the variable learning rate backpropagation algorithm with 5 hidden layers. The network is trained with 20,000 epoch over approximately 30 minutes duration. And the output of the training is tested with a random input parameter outside the training data. And the performance of the training data was evaluated with fitting to be about 90% accuracy. The output was validated with an FEM simulation using the same test parameter, and the simulation shows almost comparable stress distribution around the liver edge. So with the training output ready to be integrated with the RoboPatient platform, my current work is to obtain actual haptic information from the hardware to be fed into the surrogate model for real-time projection of the internal stresses onto the abdominal phantom. So the RoboPatient hardware includes a sensing platform on which the abdominal phantom is placed, and the RoboTour's force torque sensor are attached to each corner of the force sensing platform to provide calibrated finger positions and forces distributed on the abdomen. This information will be provided to the surrogate model in real time for the estimation of internal stresses onto the liver. And these stresses illustrated by color contour will then be projected onto the abdomen phantom as fingers come in contact with it. This process will happen in continuous loop, and the surrogate model then gets updated with the changes in the position and haptic feedback. With this integration ready, I'll perform user studies with and without the augmented real-time visual feedback to test our hypothesis: palpation training on robotic phantom with visual feedback of the internal tissues, in this case, the liver stresses, will enhance touch sensitivity in trainees compared to training without the visual feedback. Hence, it'll provide a more effective training outcome. So I'll also be adding respiratory cycle into the system for more realistic motions of organs and abdomen during training. Thank you for your attention.